Okay, so today we will start with the actually we will take a look on the midship sections, right, of various ships. By midship section, what I mean is, if you see a ship profile, it looks like this, right. So a section taken at around the mid length, that is what is referred to as midship section. Why midship section is important? Because if we see from the bending moment diagram, this is a typical bending moment diagram, which is obviously, since the ship is floating, right. So it can be considered as a simply supported beam with uniformly distributed load, right. So at its both ends, the bending moments are 0, and somewhere in the middle it will be maximum. So here I have shown a zone of 1/4 of the length of the ship aft as well as 1/4 forward, because what we see that in this region the bending moment appears to be maximum within this zone, right, within this zone of 1/4 the length of the vessel in the aft, 1/4 in the forward, we have a bending moment distribution which is on the very higher side, right. So once the bending moment is high, means it is expected that the stresses also will be high, right. That means the loading on the structure will be high, and as you know, we have already talked about it, that the longitudinal strength is one of the prime concern when we make a structural arrangement for a ship. The longitudinal strength of the ship structure is of prime concern, because it is subjected to a very severe bending moments, because of the various loading which is coming in the structure, all right. So that is how midship section takes its, basically derives its importance, because that section should be structurally sound enough to withstand the loading whatever is coming on the structure, that means to withstand that bending moment. Why? Because the section modulus which we will get from the midship section should be such that the stresses we get, right, should be less than equal to the working stress. This is the primary thing, right. So this Z is the section modulus. This Z is the section modulus of which one? Of midship section, right. Section modulus of the midship section. Because why it is important? Because there I have the maximum moment, right. So what in practice is done is that we physically draw, we do the physical drawing of the midship section, showing all the longitudinal structure members, is shown, as well as primary transverse members, and that arrangement is continued over this entire length. We have seen some structural arrangement in the forward end construction, also similarly in the aft end, also for somewhat similar reasons we have some additional stiffening arrangement. Of course, in the aft end there is one additional thing, the engine, the propeller shaft is there and the propeller is supported, so that leads to a propeller excited so called loading comes, and that loading becomes cyclic in nature because the shaft is rotating. So that gives a vibratory load such that there is no resonance taking place. The frequency of the structure has to be low. So the aft end structure is also heavily stiffened like the forward end structure, right. But this midship structural arrangement will depend primarily on the bending moment, right. It should be able to withstand the bending loads, longitudinal bending loads, right. So whatever structural arrangement is decided for the midship section, that is extended up to 1/4 the length in the aft as well as in the forward. That means over this length, that all the structural dimensions the scantlings will remain same. Not only your structural arrangements are same, dimensions are also same. That means within this length, the plate thickness, whatever is there, will be maintained constant. Though there is some drop in the bending moment, you can see from the drawing, from the curve, a typical curve we have drawn, there it is dropping, but still we continue the same bending moment, I mean same section modulus as well as the same scantlings, right. So, that is how midship section is a important sort of a drawing, from which we calculate the section modulus and ensure that for a given loading condition or for the fully loaded condition and in worst worst case scenario of wave loading, the stresses coming on the deck as well as on the keel, because they are the farthest member, remains within the permissible stress or the working stress, right. So, that is what is essentially the importance of midship section. That is one part of it. That means importance from the point of view of structural soundness, how structure it is important. On the other side, from the functional requirement, because a ship structure is arranged not only keeping in view its structural strength or structural soundness, but also keeping in view of the functional requirement. So, we will see because of the functional requirement, variation in functional requirement, your midship section arrangement for a bulk carrier, for a general cargo ship, for tanker, for container ship will be different, right. So, we will see one after another. Let us take the case of a general cargo carrier. So, general cargo carrier, we will only draw one half of the section, and we will draw a section in line of the hatch opening. That means as if I mean the section we are taking is going in between a hatch, through a hatch opening, right. So, in that case, what do we see? That we have the deck like this, right. You may have observed, whenever I try to draw any transverse section, I make the deck plate inclined. It is intentionally done inclined. It is not a horizontal deck. Whereas, when I draw a lower deck, you may have observed it is horizontal. There is inclined, this is horizontal. Can you tell from common sense why it is? I'm drawing it, means generally it is done this way, isn't it? I mean the construction also, the top deck will have a kind of a slope. This is not in the longitudinal plane, this is a transverse plane.
Yes, but if it is sloped on both the sides, then that will resist the longitudinal bend.
Okay, you mean to say that instead of having a flat plate, if it is little curved, then obviously its section modulus increases. Fine, that it will contribute to, definitely. Instead, once the plate is flat, and if I give a little curvature to this, it has a much higher bending strength, stiffness. True. If that is so, then why the lower deck is flat? It also contributes, it also undergoes the longitudinal bending. What you are saying is correct. So, by providing a gentle curvature, it does contribute to additional strength, true, but the primary purpose is something else. Drainage, simple drainage of water, simply drainage of water. There is no harm if I make it horizontal, and the necessary strength I provide by means of stiffening members, right. But it is given drainage of such that water naturally drains out on the sides. This is called camber, right. And generally this camber is, camber is, there is my horizontal, it's of the order of b by 50. There is the kind of slope given. B is the breadth molded at midship. That means the breadth at midship, 1/50th of that is the camber given. This is called camber. Right, and this, the plate has been shaped. It's a part of a parabola basically, but there is no hard and fast rule that you will have to make a parabola. In fact, from the construction point of view, I am drawing a little enlarged section such that it becomes better visible. I can even have like this. Is it visible what I have done? The central part of the deck I have kept it horizontal, flat. Only here I have made it again a flat plate, inclined. The difference between these two is it's a continuously curved plate, and here both are flat plates, it's welded here. Right. So, construction wise this is much easier. There is no bending operation involved. Right, bending operation involved. So, I can also do this. Now, depending on requirement, it can be done. Okay, in any case, that is one aspect, the deck, and then where we have a this well, whereas in the lower deck I am drawing, there is no camber needed because it's inside. There is no question of drainage. Okay. So, whenever we draw a midship section of any vessel, what we are trying to do? We are trying to show, indicate what are the structural members are there. More importantly, what are the structural members which are contributing towards longitudinal strength, right? And there is another aspect to this, why this is important, because you know, suppose you are designing a vessel, now there should be somebody to certify your design, right? Certify your design means that is needed because these are very highly capital intensive things, right? Lot of money is involved. So, if something happens, so the owner would like to have these things insured. Now, an insurance company, like if you want to get yourself insured, the company asks a certificate from a doctor, a third party, who can tell your condition about health. So, accordingly you get your insurance premium, etc. Same thing here. The insurance company will insure provided he gets a certificate from a third party, and that third party is the classification society, right? There are in what do you call, in shipbuilding, the one of the this referred to as classification society. These are the function of these societies. The function of these societies are to provide guidance to the shipbuilders towards the structural soundness of the product, primarily this. That means, because otherwise you can very well imagine that if I really want to find out the load distribution and the stresses coming, and from there I go and calculate the scantlings, that means I do entire calculations from the so called first principles, it may become virtually impossible, because loading are not straightforward, the structures are not straightforward, they are very complex geometric shape, very complex structural arrangement. So, first principles would have been extremely difficult. So, what happens? Classification society over the years, through their historical data, through their statistical analysis through using other numerical tools and so on and so forth, through research, they have come up with very simple formulae, kind of some semi-analytical, semi-empirical formulae, through which you can very easily calculate what should be the deck plating thickness, what should be the section modulus or scantlings of the deck longitudinal, and so on and so forth, right. So, that is one purpose. Using that, I can calculate very easily, and secondly, if I calculate through that, then they guarantee that your structure is safe and sound. So, from the insurance point of view, the company is also happy, they will insure your product. So, the classification society's job does not end there only. That means they may give us the guideline for the design, they may give us guideline for calculations. I do that, but in the fabrication, if I do something else, then again everything goes haywire. So, they keep a tab all throughout the process, right from the design to the delivery. They have their means of mechanism of checks. So, first point of check is drawing approval. That means they have given you a guideline, based on that guideline you have calculated, made the drawings, made the calculations. So, those things are to be first approved by them. They will check, cross check. Your people have done, the shipyard designers have done it, they will cross check it. When they say okay, they are fine, then you go for production. And in the production again, their representatives will be there who will check whether as per the design things are happening or not. Because somewhere I may show 8 millimeter, but in practice if I put 6 millimeter, because of my unscrupulous nature, so I am compromising with the product, isn't it? Such that that is not happening, those checks are there. So, in the first stage when you go for design approval, so one of the design is midship section design, right, details of the midship section. So, that is how, that is also important, because that is the so called the backbone for the longitudinal strength, right. Okay, since we have written classification society, there are various classification societies. Our Indian classification society, any name you know? Anybody heard about? What? Tell me.
Indian Registrar of Shipping.
Indian Register of Shipping. Yeah, that is the Indian version of one of the shipbuilding classification society. Any other you have heard about?
ICRA.
What is that?
I'm not sure.
No, I don't think so. Is there?
American Bureau.
Right, ABS. Right, that is American Bureau of Shipping. Then we have LRS, Lloyd Register of Shipping. This is a British one, right. Then there is GL, Germanischer Lloyd. This is a German one, right. Similarly, you have DNV, Det Norske Veritas. This is the Norwegian one. Just for the sake of, I mean, you should know these names. Then you have Bureau Veritas, French one, right. Then you have NKK, this is a Japanese one, Nippon Kaiji Kyokai, some such thing, NKK, right. There is PRS, Polski Register Statków, this is a Polish one, right. So, not necessarily all countries in the world they have their own classification societies, but many of them has. These are some of the societies which are there. What is the difference between them? As such, there is no big difference, because the final objective is same. It's only different path, sort of, right? But then still, why it is there like that? Because simply if you want to build a ship as per say ABS classification, then you have to pay money to ABS, money goes to US, isn't it? If you build as per DNV, then money goes to Norway. So, I better build as per IRS, money remain in India. That is the basic logic, why there are so many classification societies of each country. So, anyway, that is what is the business of classification societies. Anyway, so coming back to that midship, so we have seen that midship section, one of the fundamental requirement is that it takes care of the structural strength from the point of view of longitudinal bending, primarily longitudinal strength. And second important is functionality, functional requirement. Right? These are the two aspects it will look into. will automatically get structural soundness or structural requirement, satisfying the structural requirement if we properly follow the guidelines of these classification societies. And functional requirement, that is the designer's job. So, he will have to look into for what purpose the vessel is being built, because if we again little bit go back to that stage of when we talked about that these products are not, are rather always a so-called customer driven, means these are done on customers' requirement, on the basis of requirement, not a kind of a showcase product, not yet. All other products are generally a showcase kind of product. Like if you want to buy a aircraft, if you approach McDonnell Douglas, they will say we have only this range of product, you will have to choose one from them. If you go to Boeing, they will say these are the things available. But to a shipbuilder, he will not say I have this, generally will not say. He will say this is what I want, and based on that he will come up with the final product. So, what do you think he will ask for? That means a customer, what are the requirements he puts forward when he talks about, when he wants, when he looks out for a ship? Can you tell me what are the basic parameters to be told to the designer or to the builder such that, tell me, capacity, speed, what else? Budget is later. Budget will come, cost will come once you spell out your requirement. So, first you give your requirement. What do you want? You want to carry a certain amount of goods. So, capacity, but what goods, that also you have to say, the type of cargo, whether you want to carry crude or you want to carry passenger, it's different, isn't it? So, type of cargo. What else? Anything else? Do you think anything else is needed? Route. Yes, that is important, the route. What is the spelling of route? R-O-U-T-E. The route, right? Anything else? I do not think anything else. This is the basic 4 requirements. So, you can well imagine the customer has only, because he does not care, he only wants to transport certain amount of cargo through a given route, port of origin, port of destination, and via the route, right, and at a certain speed, that is all. So, from this you will have to give a solution. What the solution will comprise of? What the solution will comprise of? It will comprise of the type of vessel, isn't it? That means whether it is a container ship or a ro-ro ship or what, the type of vessel. What else? Later, it will be hull form, because that will decide your speed. I mean, decide means, well, will have a bearing on the speed, right, on the power requirement. If the hull form in the solution, the hull form, you come out with a hull form, he comes out with a different hull form, and there the, well, both are giving the required speed, say speed of 15 knots you have asked for the customer, and you are giving it at the expense of 10,000 bhp motor, and he is giving it at the expense of 8,000 bhp motor, definitely his is better. His higher power if you install means your specific fuel consumption is more, operational cost will be more. So, power, what else? Obviously, from here you will have the principal particulars. The principal particulars means the so called main dimensions. From this the solutions are coming. First and foremost, you decide on the type of the vessel, decide on the hull form and the principal particulars. In fact, first you will come to the principal main dimensions. Main dimensions are nothing but what? Length, breadth, depth and draft, right. Then when we come to the hull form, they are basically the form coefficients and the hull lines, block coefficient, prismatic coefficient, all those things, right, and the hull lines, how the lines should be. So, these are the basic two first you come to, and then subsequently you go for detailing of structural design, or maybe before structural design you write general arrangement, GA. You make a general arrangement plan, means how the whole thing will look like. This how the whole thing will look like is not is not to be misunderstood as a sort of a artist impression, not that. It is actually how the things will be laid out, not from the structural point of view, but from the functional point of view. Like where your deck house, if any, will be there, where the cranes will be located, if any. There can be deck cranes mounted on the deck. There will be your anchor handling windlass, where the windlass will be there. There will be various deck fittings, the bollards, fairleads, different fittings, where they are to be located. What will be the bulkhead positions, transverse subdivision bulkhead. So, before that you will do a flooding calculation, right, bulkhead locations, so that you know the hold dimensions. From that you do a capacity calculation to satisfy your capacity requirement, right. Then you will work out the tanks, various tank positions, where are the tanks, because tanks means what? Tanks for carriage of fuel oil, for ballast purpose, for fresh water, you will have to provide for that, you have to mention that this. So, all this in the general arrangement. Also, you will show the location of the main engine, though the final engine may not have been selected by that time, but you have a fairly good idea what will be the engine dimension, overall dimension. So, you will have to see whether that engine is fitting there, length, breadth, height, all those things. What would be the other auxiliary engines, machineries. So, all these in the general arrangement. So, you have a fairly good idea of all the components coming broadly in that. Means here you won't show details of what pipelines and what valves and what switch gears, no, broad items. These are also needed because you may need to calculate the CG location, right, for stability calculations, all that. So, once that is done, gradually it is coming to more and more, through that you refine everything, that through that you refine your length, breadth, draft requirements, because here you do the capacity calculation, you find that things are falling short, you will have to increase the length or whatever, increase the depth, so that your capacity condition is satisfied, cargo type condition is satisfied, right. And the hull form, at that stage it is only whatever will provide you the minimum resistance, right. Theoretically whatever you are getting, you come to that hull form, so that speed condition expected will be satisfied, provided providing required power. So, then comes the structural design, right. And in this structural design, then you start with the so called scantling calculations. That means, up to the stage 3, once stage 3 is over totally, your design, your hull lines, the form of the vessel, the principal dimensions, everything has been have been frozen. You are not going to change that. Now you have started detailing on that. First phase of detailing is the so-called to do that you need to do the scantling calculations. Scantling calculations means you start with calculating the plate thickness, section dimensions, stiffener dimensions, etc. for the entire shape. Once that is done, right, then you start with the midship section drawing. Physically layout, you draw the thing. Well, if you do not draw also, there is not a problem, provided you have all the structural items, whatever is going to come in the midship section, you have calculated for them, and you are going to calculate the section modulus, right. But it is worthwhile to draw, because that will be needed for physical approval of the classification society. You will have to send the actual drawing, because in drawing it will be physically shown. Instead of writing in words that the deck plating thickness will be 30 millimeter and it will have 40 longitudinal, because that becomes vague, then you have to write many lines, because in way of hatch opening it will be different, and so on and so forth. So, instead you draw it and show, right. So, that is how in the structural design stage, your after scantling calculation, one generally it starts with the midship section drawing, right. So, depending on the cargo type or the type of the vessel, your midship section arrangement will be different, because that is what is for the functional requirement point of view. So, when it is a general cargo carrier, the arrangement is somewhat like this. Basic preliminary arrangement, the moment you are talking about any type of a vessel, when you start the midship section plan, the basic thing is done is that the outer hull is drawn, the main deck is drawn. If there is a hatch opening, you draw it showing this particular line I have drawn, that is what is the hatch combing, that means there is a hatch opening here, right. And then immediately you draw what is called is the inner bottom plating, because all ships, ocean going ships, they have a double bottom. We have talked about double bottom. All ocean going ships have a double bottom. So, immediately one starts with the outer hull, the main deck and the double bottom. This is a must for all vessels, more or less, right. And now, when it is general cargo ship, generally general cargo ship has at least one lower deck. So, you draw one lower deck, and whenever these decks are there is a hatch opening, right. The moment there is a hatch opening, you have a hatch side girder. So, you draw a hatch side girder, right. Same thing will be there in the lower deck also, hatch side girder, and then the decks are what? Longitudinally stiffened. So, you can show some of the longitudinals. Schematically, some longitudinals are shown. Right. Same thing is true for the lower deck. You can see one thing, the flanges of all longitudinals I have shown going outward, right, but the last longitudinal flange is inward. Why? Such that bracket connection is made easy, because you will have, it has to be bracketed to the side shell stiffeners, whatever the stiffener be, whether it is a longitudinal or transverse, it has to be bracketed because of a better load path, because of better connectivity between the structural members, right. So, it is turned, the flange is on the other side, such that the back side of the wave is available for proper bracketing, right. So, this is done, immediately you go for the double bottom. Double bottom construction we have already talked about in detail, they are identical for all type of ships, right. So, and they are also longitudinally stiffened. So, we have these bottom shell longitudinals inner bottom longitudinals, and so on, right. It goes through this. We show that there is a here in line with the hatch side girder, we can provide a side girder, right, and then you have the longitudinals. By making these thing, we indicate that there is a plate floor. So, the double bottom is drawn, and also to be more accurate, make this a firm line indicating that we are given a central line girder, right, and then make these small lines, the scallops, right. One or two these openings you can show schematically, that indicates the plate is cut there, plate floor. For the longitudinal to pass through, we have shown the detail of these drawings, and draw these dotted lines which indicates that the struts are there. This is a side girder, right. So, now there is one term called intercoastal. The thing is, the center girder is generally taken to be a continuous longitudinal member, means the floor plates come and end at the center girder. Again, from the other side, this is my port side view. On the starboard view, the plate floor starts from here, right. Side girders are generally made intercoastal, that means between two plate floor the side girder continues, right. What does that mean? That means that would be visible in a longitudinal section. The longitudinal section is, say, I am drawing the only the, say this is my double bottom, it is done little exaggerated. Say this is my double bottom, and let us assume these are my transverse subdivision watertight bulkheads. Say there are only 3 holes, right. And let us assume these are my plate floors. Say there are, let us assume 2 plate floors in this hole, which is never so, because there will be several of them. Now, the thing is, this side girder, the center girder will be a one continuous plate. By one continuous plate means what? The ship length could be 200 meter. So, we do not produce 200 meter long plates. It will be only 10 meters. So, 20 of them will be put one after another, and they are welded. Not at one go, but in blocks, in units, that is a different issue. The whole point is they are continuous, means nobody is penetrating them. But the side girders will be like this, that this is one side girder, this is another side girder, like that. That means they are from floor to floor. That is what is called intercoastal. Intercoastal, from one floor to another floor, the side girder is there. That means the floor is continuous and side girder is coming and ending at the floor. Floor is continuous from the side shell to the center girder or to the duct keel side girder, if there is a duct keel kind of arrangement. So, there are 2 girders. So, the floor comes from the side shell, from the bilge to the girder, and the side girders, longitudinal girders, they will be continuous from one floor to another floor. That is how the constructions are done, and these side girders are generally not watertight. We will see later some of these drawings which will make it more, I mean some of the photographs which will give you a much better clear picture of the entire thing. So, here we get the double bottom, because for any ship you need a good flat surface for storage of cargo. So, it has to have a double bottom. That is one of the functional requirement. Another, from the pollution like liquid cargo, you do not need a double bottom because liquid can go anywhere, but from the pollution control point of view, a double bottom is mandatory for oil tanker. Okay, so once this is done, so my bottom shell is done, what do you call the double bottom, the deck, but here we have shown the deck longitudinally stiffened. Now we have said that these longitudinals should have supports, because otherwise the length of longitudinal will be from one bulkhead to another bulkhead, right. Say the deck is longitudinally stiffened means what? A longitudinal stiffener is running like this, right. It is piercing through the bulkhead, and then the transverse bulkhead will be sealed off by those plates, as we have shown, right. So now in such a case, what it appears? It appears as if the longitudinal is supported between these 2 points, because they will be welded at the bulkheads. So the span of the longitudinal will be this much, and you know the bending moment is square of the span, right. So for a given loading, if this is my span, the bending moment on the longitudinal will be very huge. If that is so, to keep the stress within the limit, your section modulus of the longitudinal will be very huge. So that is not a very wise thing to do, because then the depth of the longitudinal may come up to this, isn't it? So what is done? You will have to have transverse members which will provide additional support. So something like this. Obviously, the scantling of the transverse member has to be more than that of the longitudinal, because the transverse member is providing support to the longitudinal, right. So that transverse member would be like this. What is this red line I have drawn? This is one of the deck transverse. This is called deck transverse. It will be situated at certain intervals, as I have shown. At what intervals? At what intervals generally they are? Any idea? I have told you possibly. What are the intervals of the plate floors? 3 to 4 frame space, same interval, because the whole idea is you form a ring like a structure. Ring like a structure means a plate floor, side shell a wave frame, a deck transverse. In between plate floors you have bracket floor, normal frames, no deck transverse, right. So that will be better visible in a plan view. If I draw the deck plan, suppose this is my let us say these are the bulkhead positions, and this is my deck plan. You have the hatch openings here, right. Your this is the hatch side girder is running like this, right. You have the longitudinals, they are spaced as per the frame spacing, right, and the transverse members are here. You have one hatch and beam, there is another hatch and beam, and say another transverse. So the spacing between the transverse would be 3 to 4 frame space, 3 to 4 frame space, right. So this transverses will provide the support. So again the same thing here, you will have this small, these so called openings, like in the floor you had the same connections. Here the intersection of the inner bottom longitudinal and the floor plate, or the intersection of the bottom longitudinal and the floor plate, whatever is the detail we have already discussed about it, will be same here also, right. So, they are supported. So, same thing will be there for the lower deck also. So, you see, when I am trying to draw a midship section, we are not drawing it through, well, it should have this, it should have that, not from memory, but from logic, right. That is what you try to see, that whenever you are going to make a midship section arrangement, say a bulk carrier, we will come to bulk carrier later, you will see that we will be doing it through some logic, instead of memorizing that, well, bulk carrier should have this type of arrangement. Then if you forget, then something you will miss, right. So, all these arrangements are done not that it has to be this way, but it is better to be this way, because that satisfies my logic, my logical requirement. Logical requirement is should provide me the required strength, should provide me the required functionality, right. So, now, and that logical requirement tells me that the double bottom should be longitudinally stiffened, decks to be longitudinally stiffened, because we know longitudinal stiffening arrangement provides me a better buckling strength, thereby I attain a better strength to weight ratio. So, that is a better way of doing things, we are doing it. So, in the same logic, my side shell also can be longitudinally stiffened, but here we will see we will not do longitudinal, but we will do transverse framing, transverse stiffening, right. And the transverse stiffeners would look something like this. That means, in the side shells are transversely framed. They are in the transverse plane, isn't it? Like that of the deck transverse in red we have drawn. They are in that plane, right? And they will be obviously connected to each other by provide bracketing arrangement. And also bracket here, suitable bracketing arrangement. So, now we see that our this midship section is fairly complete. We have provided for ample structural member to contribute towards longitudinal strength. What are the members? Well, the shell itself, then the hatch side girders, decks longitudinals, inner bottom longitudinal, bottom shell longitudinal, center girder, side girder, all these are longitudinal members, and longitudinal members contribute towards longitudinal strength. So, we have sufficient of them, and also we have the transverse members in the transverse plane. What? We have the plate floor, we have the side shell frame, we have the deck transverse, right. So, they will, this deck transverse and plate floors, they are providing support to the longitudinals as well as providing transverse strength in the transverse plane, isn't it? They are providing for the transverse strength. So, we will have, this particular arrangement provides me with required, apparently provides me the required strength, because we started with the strength requirement is to be satisfied for longitudinal bending against transverse deformations, torsional and local, right. So, this is satisfying, I mean this appears to be satisfying in both transverse and longitudinal. Now, the thing is whether it is truly satisfying the longitudinal strength or not, we will have to do a calculation. So, what is that calculation? That calculation essentially involves finding out the neutral axis of the section obviously while doing the calculation I will take the full section, right, the full section of, because the whole section will contribute towards the strength. So, finding out the neutral axis and finding out the section modulus of this. How do we get that? Well, we get from, to that we will take only those longitudinal members. Obviously, this deck transverse side shell frames will not contribute. Naturally, they are not contributing towards longitudinal strength. So, their section modulus does not come into picture, right. So, through that we will calculate, and obviously that is calculated in way of hatch opening, because where hatch opening is not there, the plate is continuous, as well as you have so many additional longitudinals also, but you do not take that, because firstly the longitudinals may not be there, there can be transverses. We have talked about the cross deck structure, and that plate is small between the two hatch openings, so they are not contributing towards longitudinal strength. So, thereby we find out the section modulus about the neutral axis, I mean moment of inertia about the neutral axis, and then divided by y deck or y keel. Y deck is this, right, and y keel is that its counterpart. Y deck is always bigger than y keel, because you have a higher concentration of structural members below. So, this is always the minimum value. So, this is my so called Z deck, the section modulus for that deck, I mean section modulus of the section with relation to the deck plating. You have the bending moment distribution. So, divide that by this, you will get the stress value. If that stress value occurs to be higher than the working stress, what you should do? What has to be done? That may happen. All this you have done by taking the scantling from the classification rules, calculated and put. Based on that, you have chosen the dimension of deck longitudinal, based on that you have chosen the thickness of the inner bottom plating, etc. But after doing that, you have done the calculation of I about the neutral axis divided by this, and you find the stress which is coming, right, is more than the permissible stress. So, then what is to be done? What to do? That is not permitted. You will have to keep the stress below this, means you have to increase this. Z deck has to be increased, or in other words, INA has to be increased, means you will have to take a relook at the arrangement, and you will have to see that, well, scantlings are to be increased. Now, which one is to be increased? Those decisions are to be taken. It is better to increase at the deck level, which is furthest away, that provides for more section I value, right, all that. So, that is how, so 1 or 2, 3 iterations may go till you get the final scantlings of all the things, right. Well, the side shells are transversely stiffened. Why it is so? Please try to think about it, because you have told that it is better to have longitudinal stiffener, I mean longitudinal stiffening arrangement, but here we are saying that no, for general cargo shape, side shell will do transverse stiffening. There should be some reason. What is that reason? Think about it and tell me in the next class. Okay.